Hi, I'm Christian Ramos, and this is my uh, presentation for Physics 2211, Section K, Lab 1, Constant Motion. So the objectives of this lab is to apply Newton's first law to a real-world scenario by rolling a ball with a constant velocity and no net force on the ball, and filming it and then tracking that data. And Newton's first law for information needed is an object at rest remains at rest, and an object in motion remains in motion at a constant speed in a straight line unless acted on by an unbalanced force. So if there's no net force on the ball, it will remain going at the same velocity. So some of the concepts that we'll be talking about in this video are constant velocity and Newton's second law, which are actually very related. So when the net force is equal to 0, the velocity is constant, and Newton's second law says that when net force equals mass times acceleration, so because the system, the object, the ball, whatever is moving has a mass, and net force is equal to 0, therefore acceleration has to equal to 0, and because acceleration is equal to 0, then there's no change in velocity. In the velocity update formula, final velocity equals initial velocity plus net force over mass times change in time, because the net force is 0 and the acceleration is 0. Acceleration equals net force over mass. Therefore, the final velocity should be equal to the initial velocity. And then the position update formula, final position equals initial position plus average velocity times change in time. Since the average velocity is consistent, then as we move through equal time increments, then the position of the system, the ball, or the object should be moving with equal magnitude per equal time increment. And then average velocity, we'll talk about more later on in the video, is initial velocity plus final velocity over change in time. So as you can see on the screen is the tracker data, and on the tracker I made the positive x-axis on the right side of the origin, the negative x-axis on the left side of the origin. So as you can see, the ball is moving on towards the negative x direction at a consistent velocity. There's a small net force being applied to the ball, but we'll disregard that for now and talk about that later. So we'll just say that there's no net force being applied to the ball. And as you can see on the graph on the right-hand side, it's a consistent slope in the negative direction, showing that the ball is moving at a consistent velocity in the negative direction, and that the position is changing equally per time interval, which is 1 frame of the video. So here's the computer model, the predicted motion simulation, and here is the same motion being applied on the ball. I'm just going in the negative x direction, but here there's really no net force being applied, so the velocity is consistent, which is why the position versus time graphic is a perfectly negative sloped line, perfectly linear negative sloped line going in the negative direction. You can see, and then the velocity will be one constant velocity with a change in velocity being 0. So here's a comparison between two different models, one with the computer model being with the initial velocity and one with the computer model being the average velocity. As you can see, the one with the initial velocity is here, and you can see it as a vector of negative 0.95 meters per second, and the average velocity is negative 0.82 meters per second. And the average velocity was taken using the final velocity and the initial velocity, which is taken between two different points at the very beginning and the very end of the tracker video. And it's shown that the tracker video actually has a lower velocity because the force of friction is actually acting against the ball in motion. And this is a net force in the opposite direction of the motion, so it has a change of velocity which is negative, and that's why it has a lower velocity. Now, the average force used in the simulation helps bring the two lines a little closer together, because it does account for the final velocity being slower than the initial velocity due to friction, but it still doesn't do it well enough to have friction throughout the entire time. And then obviously with the computer simulations there's no net force, so the velocity will be a greater in magnitude. So here's some of the observations I made, are very similar to what I said in the last slide, is that the real-life model is slower than the computational model due to the frictional force acting against the tennis ball. Due to this force, the real-life model has net force and a change in velocity and acceleration. The computer model does not have a net force acting upon the tennis ball, so it does not have a change in velocity. And then underneath, I have some force diagrams with the computational model with normal force and gravitational force, and then the real-life model, which includes force of friction acting against the motion of the ball. So what if we flip the x-axis and the ball rolled in a positive direction? This would end up in pretty much the same results with the ball, as you can see below, rolling in the positive x direction to the right. It would have the exact same slope in terms of magnitude, but it would go in the opposite direction because it would have the same initial force pushing the ball, getting into its initial velocity, and then that initial velocity would just have the ball go in the same speed but different velocity because it's going in the opposite direction, in the positive direction instead of the negative direction.